Hello everyone, welcome you all in my YouTube channel Engineering Guru 2020. In this video, I will cover Otto cycle. In this video, I will focus on how to draw PV diagram, then understand the four process of Otto cycles, and final efficiency of Otto cycle. Let's see one by one. Otto cycle is an ideal air standard cycle for petrol and gas engines. It is also known as constant volume cycle as the heat addition take place as a constant volume. Focus why Otto cycle is also known as constant volume cycle because heat addition take place as the constant volume. So that's why it is also known as constant volume. It consists of two constant volumes and two reversible adiabatic or asymptotic process. Let the engine cylinder contain 1 kg of air at point number 1. So in Otto cycle, 4 number of processes are there. It consists of two constant volume and two reversible adiabatic or asymptotic process. Now let's see one by one. First, reversible adiabatic asymptotic compression. This is process number 1 2. The air is compressed asymptotically from state 1 to state 2. The pressure and temperature increase whereas the volume reduce. In this process, no heat is absorbed or rejected by the air. Here, this is PV diagram. On x-axis volume and on y-axis pressure. This is point number 1 and this is point number 2. So the pressure and temperature increase. The pressure and temperature is increased from point 1 to 2, whereas the volume is decreased. As you can see that the volume is decreased, or we can say reduced. In this process, no heat is absorbed or rejected by the air. So this is called adiabatic process. PV raised to gamma equal to constant. Second process. Second, the constant volume heat addition. Process 2, 3. During this process, the heat is added. During this process 2, 3, heat is added at the constant volume from state 2 to state 3. The pressure and temperature of the air increase. Here you can see that this is point number 2 and this is point number 3. Here the heat is added. You can see QS. Heat is added during the process 2, 3 at the constant volume, and the pressure and temperature of air are increases. You can see that pressure is also increased and temperature is also increased. Heat supply QS equal to CV T3 minus T2. T3 minus T2. So from this we can calculate the heat supply during the process 2, 2 and 3. Now process 3, the reversible adiabatic or asymptotic expansion process 3, 4. The air is expanded asymptotically from state 3 and state 4. The pressure and temperature decrease whereas the volume is increases. In this process, no heat is absorbed or rejected by the air. We already see the first process, first and second, and process 2 and 3. First and second process, that is the reversible adiabatic or asymptotic compression, whereas the constant volume heat addition process number 2 and 3. In first two steps, pressure and temperature are increases, but in process step number 3, in process 3 and 4, the pressure and temperature decrease where the volume is increases. No heat is absorbed or rejected by the air. So here this is point number 3 and this is point number 4. pressure is decreased from 0.3 to 0.4. It is also called adiabatic process. PV raised to gamma equal to constant. Now final step, the step number 4, constant volume heat reduction process 4.1. During this process, heat is rejected at the constant volume from state 4 to state 1. Pressure and temperature of air reduces and reaches the initial condition. Thus, the cycle is completed.
First, open YouTube and write down Engineering Guru 2020. Search. This is Engineering Guru YouTube channel. Open this and subscribe this for more update. Various playlists available here. You can see this is for various subject. This is for velocity diagram, uniform velocity, for cam profiles, synthetic linkages, and more playlists are here.
So during the process 4.1, the heat is rejected as the constant volume, and pressure and temperature of air reduces. Here you can see that this is 0.4 and point number 1. So pressure decreases and volume is constant. Heat rejected QR. This is heat rejected QR at constant volume heat reduction. QR equal to CV T4 minus T1. So this is the formula of heat reduction. So we already covered 4 steps and 4 process. Process 1-2 means this is for reversible adiabatic or asymptotic compression. Process 2-3, this is for constant volume heat addition. Process 3-4, this is for reversible adiabatic or asymptotic expansion. And final process 4.1, this is for constant volume heat reductions. So heat is added during this process 2 and 3 at constant volume, and heat is rejected at the process 4.1 with a constant volume. Now next step, that is efficiency of Otto cycle. So net work done, W net equal to heat supplied minus heat rejected. As we know that heat is supplied during process 2 and 3 and heat is rejected during process 4.1. We already derived this formula, CV equal to T3 minus T2 minus CV T4 minus T1. As standby efficiency equal to net work done divided by heat supply. So net work done equal to CV T3 minus T2 minus CV T4 minus T1 divided by heat supply. This is process 2-3, CV T3 minus T2. So we can write 1 minus T4 minus T1 divided by T3 minus T2. This is called equation number 1. Compression ratio R is defined as R equal to volume before compression divided by volume after compression. So we can write V1 divided by V2. Expansion ratio is defined as the ratio equal to volume after expansion divided by volume before expansion, equal to V4 divided by V3 equal to V1 divided by V2, equal to R into bracket V4 equal to V1 and V3 equal to V2 from the PV diagram. For asymptotic process 1-2, this is asymptotic process 1-2, T2 divided by T1 equal to V2 divided by V2 raised to gamma minus 1. This is for process 1-2. So we can write T2 equal to T1 R raised to gamma minus 1. This is equation number 2. For asymptotic process 3 and 4. For this process, we can write T3 divided by T4 equal to V4 divided by V3 raised to gamma minus 1, R raised to gamma minus 1. So T3 equal to T4 R raised to gamma minus 1. This is equation number 3. Substituting the value of T3 and T4 from equation number 2 and 3 in equation number 1. Now simplification is done. Efficiency equal to 1 minus T4 minus T1 divided by T4 r raised to gamma minus 1 minus T1 r raised to gamma minus. Efficiency equal to 1 minus T4 minus T1 divided by r raised to gamma minus 1 into T4 minus T1. So final efficiency of the Otto cycle, it would be 1 minus 1 divided by r raised to gamma minus 1. This is equation number. From this formula, you can find the efficiency of Otto cycle. The efficiency of the Otto cycle depends on the compression ratio and specific heat ratio. For the particular medium, the variation of gamma is negligible, and therefore the efficiency of Otto cycle increases as the compression ratio increases. Figure shows the variation of air standard efficiency with compression ratio and gamma of the working medium. Here you can see that this is compression ratio R and this is efficiency. This is for exhaust gas, gamma equal to 1.3. This is for air, gamma equal to 1.4, and this is for monoatomic gas, gamma equal to 1.67. Usually compression ratio of 6 to 10 is used for petrol engine. So if you find my video very helpful, you can subscribe our YouTube channel. You can follow on FB page, join us on Telegram channel, WhatsApp channel. If you find my video very helpful, you can like, comment, share and subscribe my YouTube channel. Stay on this channel, more video will be come. Thank you.